Okay, so here's a little intro video on solving trig equations. We've been solving basic equations for a long time, and this is the same general idea, but now we're going to have trig functions involved. So we were working in sections 1 and 2 on identities, but now we're going to conditional equations, which are only true for some values, which is like most of the equations that we've solved. So an example would be like 2x minus 5. Right? This is only true when x equals 7. So we're used to seeing things like that. Trig equations, most of them follow along the same rules, but we might get more than one answer, right? And to show this, let's think about the graph. So for example, if we were solving cosine of x equals 1/2, graphically, we can see our answers here. I have in the blue line y equals 1/2. And that red line is my cosine graph. So anywhere these intersect, those are going to be all of our answers, right? And it goes on forever. So thinking about where cosine actually equals 1/2, the graph is helpful, right? But those aren't really perfect values. So I also like to think about our unit circle. So I only drew the right half because cosine is positive in quadrants 1 and quadrants 4. And if you're thinking of our unit circle coordinates, I get 1/2 up here at 60 degrees or pi over 3. And there's a lot of ways we can write that, right? We can write it as 60 degrees. If we went around the circle again, it would be another 360. So like 420 degrees would be another answer. And then that would be that value on the graph. So that would be our pi over 3. Like over here, this would be negative pi over 3, also represented by this point down here on our unit circle. So there are lots of answers, and as long as we can find the values or the spots in our unit circle, that's a good way to go. So we can write our answers in the form of an equation. And we've been kind of doing this with our domain and range. So cosine of x equals 1/2 when a couple different ways we can write our answers, right? In this first quadrant, when x equals pi over 3, or any coterminal angle with that, right? I can go around the circle as many times as I want, so I can add 2 pi any number of times. So where n is an element of the integers. Now that's just one answer, right? Because we also went into quadrant 4. So this guy, we already wrote an equation for, pi over 3, and we would get like the next value over here that isn't seen. But negative pi over 3, right? That's not 2 pi. That's a smaller distance. So I can write another equation to include our negative pi over 3 value. So x equals negative pi over 3 plus 2 pi. And that would cover like these 2 points and all of those coterminal angles. So there are an infinite number of solutions. I could pick any solution and write it there. Like for this point down here, we also could have called that 5 pi over 3 instead of pi over 3, right? That would produce an equation that would hit those same values. So these would be our solutions in the form of an equation for this problem. Now for every problem, there also would be a way to write your solutions as one equation. So for this same problem, I'm going to just show an example of that. If we have cosine of x equals 1/2, just like that last one, if I wanted to write my solutions, oh gosh, what a horrible unit circle, but we get the point, as one equation, for this one, I could kind of be a little lazy. And since we had positive pi over 3 and negative pi over 3, I could write my answers like this. All right, so let's get practice actually solving some of these. So to solve trig equations, we do it a lot like a normal equation in algebra, except now we're going to have our trig functions. So the first thing we want to do is isolate the trig expression. So I'm going to put two problems out here. And you guys should take a second if you want. I might pause my video and you can kind of work along, or if you want to just see how I do these. I'm going to isolate the trig expression. So pretend our variable here is tan x. So I'm going to subtract my tangent over to one side and add that root 3 on the other. So I get tan x equals root 3. For the other one, we have a sine squared. I'm going to start just by isolating that guy. Sine squared x equals 3/4. And then I do have to take one more step and square root both sides to get sine alone. Don't forget, when we take a square root, we need our plus or minus. So my isolated answer here would be plus or minus root 3 over 2. Now we're thinking along the lines that we did in that first example. So I'm thinking, and I like to use the unit circle for this, so it's really important that we're pretty comfortable with our unit circle here. So where does the tangent equal root 3? So sine over cosine, I want that to be the point where we have root 3 over 2 and 1/2, which would be up here at pi over 3 again. So I'd have 1/2 for my cosine, root 3 over 2 for my sine. So if I took sine over cosine, that would give us root 3. The other coordinate would be down here, right, where pi over 3 is my reference angle again. Both of these are negative. So that would be our angle 4 pi over 3. To write my answers, I'm going to write them as an equation. So I can say x equals, now for tangent, we could do two things, right? Tangent's a little bit different than our other functions. I'll get answers every pi units, since the period of tangent is pi. So if you remember that, we can always write one equation for tangent, pi over 3 plus pi n. Not a big deal if you didn't remember that. We could also write our answers in the form x equals pi over 3 plus 2 pi n. That would cover all the terminal angles for pi over 3. And then x equals 4 pi over 3 plus 2 pi n. So that's just saying that angle and all the coterminals. So either that red or the blue, either of those would be acceptable. For this second example, we're looking for where the sine is equal to positive or negative root 3 over 2. So I guess I really liked pi over 3 for these, right? That's our same coordinate that we had over for our tan right there, which I pretty much highlighted over. So it's going to be all of those reference angles in our unit circle. 2 pi over 3, 4 pi over 3, 5 pi over 3. So I try to be efficient here and not write 4 separate equations. 2 pi over 3, 4 pi over 3, 5 pi over 3. But you absolutely could. I could say pi over 3 plus 2 pi n, 2 pi over 3 plus 2 pi n, 4 pi over 3, etc., etc. But I can be a little more efficient on this. So the first way would be just to write 2 equations. I could say, for example, pi over 3 plus pi n. That would cover these two, right, going halfway around our unit circle. And then I could say 5 pi over 3 or 2 pi over 3, doesn't matter which one, plus pi n. Again, I'm thinking of how far these are in our unit circle. These are pi apart. Or we can use one equation to describe these. So I'll use, I don't know, my orange marker over here. I could just say x equals plus or minus pi over 3. Try to erase some of these values in here. Not going to be good. I'll do a new unit circle here. So positive and negative pi over 3 would cover my first quadrant and my fourth quadrant. And then I could just say plus pi n. Because if I add pi to pi over 3, that'll put me in quadrant 4 at our 4 pi over 3. If I add pi to negative pi over 3, that would put me in my second quadrant at 2 pi. Got cut off, but I have the negative pi over 3 plus pi over 3 would put me in my second quadrant and cover 2 pi over 3. So we're just making sure that all of these values in our unit circle can be covered, either 4 equations, 2 equations, 1 equation. As long as all of our answers are covered, then we are good.